Welcome to another GCBASIC tutorial for the PIC18FxQ35 chip family, part 14. This is Pulse Width Modulation, or PWM, many ways. Just want to show you there are many different ways that you can generate a signal for pulse width modulation. We won't even cover them all. I'm sure we can think of more. So please like this video and subscribe to the channel. So we're going to dim some LEDs, but we're actually going to put an oscilloscope on this as well. So we're going to use these PMWs many ways, and we'll just see the LEDs respond and the oscilloscope. So I'm using this board. I'll go out to the camera straight away, almost immediately, right? But look, you can't really see it because I've got my little oscilloscope here, and I'll introduce this in a minute. But this is the general board, and we're going to be using some LEDs and a potentiometer here. In terms of where the LEDs are attached, there's a very good reference schematic in the PDF. And basically all we've got is 4 LEDs, and they're brought to the port and down to ground through junction 6, which is set, and I have applied a VDD-IO to what was called RC7. But it's not, it's actually pin 18. Right, so let's just talk about that. I've applied what voltage? I've got 5 volts applied to here. No VDD-IO power, no domain IO, and I am using some of those domains. Not really, I'm not this time, but I'm banging on about this, okay? So let's look at pulse width modulation. It's basically a simple succession of pulses, and you actually average reduces the average power delivered by an electrical signal. It chops it up into discrete parts. So it's the average of a value, and the load is controlled by turning it off on and off at a very fast rate. The diagram shows a fixed frequency change in duty and how that blue line represents the average power. Now, that means that the total power is going to go up and down. So for an LED, it would flash on and off as the different duty cycles. And that's what we're going to be doing a lot of. We're going to be using many different commands, from really basic commands to really complicated 16-bit stuff. And we'll just be generating a square signal that looks something like that. My oscilloscope will show us whatever it shows, but we have different methods. Now, you saw on my screen, when I showed the camera, I am using an X-Mini Lab, which looks, you can get them from the Gabtronics website. Look, I'm using X Protel Lab here. I bought this, it's fantastic. It's my go-to device, but I'll show you something else as well. And I've got it hooked up almost like that there, and it's sitting here. I've got a signal coming in from one of the LEDs that we'll be working on. That diagram on the PowerPoint doesn't represent the signal we're generating because that's a sawtooth. So, pulse width modulation, we can do it many different ways. I'll bring the pen up. We have a real simple way, and I'm going to just take you through the table. I'm going to show you 7 in this, 7 here, 6, sorry. And look, this is the type. This is the characteristics, whether you need PPS or not, and just a general comment, okay? So we have a command which is a really simple way. We can just turn the port on and off. That will generate a square signal, and you can do that on any port that is valid, okay? All right? Can't do it on every port, but you can do it on a lot of ports. We have a command that's called PulseOut, and you can pulse out on a port, any port that's valid, and you don't need PPS. Fantastic. We have a command called PWMOut, and you can send out a number of pulses. You can do that on any port, no PPS required. So we have 3 ways of generating a signal that does not require the PPS to be set. Then there's compare PMW method. This requires PPS. You need to set the CCP module, And we have a method which is called, I call it fixed frequency, because you can control that fixed frequency very easily. You set two constants are set. It's very low impact in terms of the code, but it is fixed, and you can turn it on and off, and it's using CCP1. Really very, very simple. It's a fixed frequency, fixed duty using timer 2. There we go. You've got another method which uses the same CCP module, therefore you need to set the PPS, variable frequency, variable duty using timer 2. Now there are other valid timers, but I'm going to use timer 2. And assembly does all the heavy lifting for you. So somewhere in a library, all the heavy lifting is done for you. So it recalculates all the things that need to be recalculated, and it does quite all the heavy lifting. Then it's a module, whole module on this chip called the PWM module, has its own timer, and it has a huge range of capabilities, and I'm going to show you how you need to set that up. There's lots of parameters. You need to set the PPS not for the CCP, but for PWMXX. And I'll explain that later on. And then there is other methods using a timer, which I will come on to in another video, but for today, just do the 6. So we're going to walk the examples, and then, then we're going to view the results on the X Minilab scope. So let's go directly into GC Studio. Let's go. We got some code up. Oh, good. Oh, I've been doing other things. Look, I'm going to open the folder, and it's in the vendor boards. Your demo folder, vendor boards, microchip, PIC18F2 plus board 2010 18F. Select the folder, and we're in. And it shows us the IDE. Zoom in. Okay, let's just do some really simple stuff to get this thing going. I'm just going to ask you to open up 241, which is pin IO. And all this is going to do, I am not going to even show you some of the header stuff, because I'm assuming that you've set the chip up and you've got a constant called LED3, and all I'm going to do is turn it on and off. And if I program that, an LED on the camera, let's have a look on these 4 LEDs are at the top of the picture where my mouse is, should have come on, but they haven't. I'll tell you why they haven't come on. I haven't power cycled this chip since using PPS. So because I don't set the PPS to 0, I need to power cycle the chip, which I will now do. And you can see I have an LED that's on here. It just came on. Power cycles, and it's actually flashing, but you can't see very much. So let me plug in my oscilloscope, which was not plugged in because I've been away on a bike ride. Turn my oscilloscope on, and you can see Gabtronics and a signal. But on my PC, I can type in Gabtronics, and it's actually showing me the same signal. Look at that. That is cool, is it not? Let me put that there. Look at that. We got a signal. And that signal, by the way, is 38 megahertz, because I'm just going to use 38 megahertz all the time. So do we need the picture on the oscilloscope? We do. We'll come back and forth from this, okay? Now, I'm going to leave, let me just think how to do this best for you. That's okay. We'll leave the oscilloscope the way it is. So that was 241. All it does is put in, turns the LED on, waits 12 microseconds, and then does a load of no-ops, but it is doing 38 megahertz. It's a method. Let's look at PulseOut. I'm assuming you've got a constant called LED3, and it's going to do a PulseOut. It's going to pulse it out for 12 microseconds, and then wait 12 microseconds, and it will put a pulse out, okay? Let's have a look what happens on the oscilloscope. You'll see it flash as it programs, and it's doing it 38 megahertz. How is it 38 megahertz? Because a 38 megahertz is a 12-second delay. So if you wanted to do 50 signals, you could do it using PulseOut. PulseOut generates signals. It generates a signal based upon the time delay you've given it, which is the second parameter, for a given amount of time. That's it. That's all it does. It's brilliant. Works really well. 43. 243, using something called PWMOut. Let me explain this. PWMOut, if you look at the little bit of syntax I've given you here, it has a channel, a duty cycle, and then the number of cycles. And what this does, it's an arbitrary number just that I've used today, but it will it will have a channel, no PPS involved in this, and it will just say what the duty cycle is and how many times you want to send it out. So in my example here, I'm saying PWMOut on channel 1, 127, which is actually the duty cycle, because it's a byte value. So 127 over 255 is 50. Is it? 50%. You work it out. And I'm saying send out 4 signals. How did I determine the channel? I have a constant up here called PWMOut1, and I've set it on LED 3, which is the same LED I have my oscilloscope on. Let's program that. Look at the oscilloscope. I'm going to change the and in here, look at that, I got 4, exactly 4, which is what PulseOut does. And it sends, and this is the loop in the code. So if you wanted to send out 4 pulses for something, like a stepper motor, this could be very useful to you. Because if all you need is 4 signals, you can send out 100, 10, 1. Depends what you want, but no, there's no PPS involved. It's you set the constant PMW_out1 to a specific port. You actually can have a delay after this sequence has occurred, but look at the help. It's a way of generating a signal. Number 4, 244, using fixed mode. Fixed mode. You set the port to an output, and these are the 2 constants you set: PMW frequency, PMW duty, and a command, PMW on. And I'm just doing a do loop here because I'm using a hardware module. So that hardware module is going to require the PPS. And the PPS on this one is called the CCP1. I think there's 4 in this chip. Let's have a look. Let's press function key F4, PPS tool. And in here, I can go there's 3, look, CCP1, put it on B0, and I can add it in. It's as simple as that. And I've added all into here on the same channel. So they're all sitting, all 4 LEDs will light, and we'll see that. So all this does, so that connects the CCP signal to those output ports, and so all 4 ports are going to show us the CCP1, which is compare PMW. Recap, I'm going to set the frequency, set the duty, and turn it on. There's a bit more down here. If you want to have a look, you can have a play. I don't know. You can go and have a play. Let's look in here. We're going to have to change the signal here. I think that's 38 megahertz. There you go. 38 megahertz. If I zoom out on there so you can see it, it's my scope can't cope basically. There you go, 38 megahertz. And you go, ooh, it's not really, that's not 50%. I'll tell you what we'll do. We'll put it to 25. If I had a proper oscilloscope and with more frequency, I'd be able to show you a better square wave, but that's life for today. So I have set the PPS for the CCP1 channel, and those 2 constants determine the setup. PMW on and PMW off do the command for you. That's it. I think in the assembly, it's very small. Let's have a look at the size of the program. The assembly to do that is 111 words. Oh, so sorry, 92 words, and that's doing all the serial stuff as well. So it's tiny, very low impact in terms of assembly, because all the heavy work is done in scripts for you. 245, we're going to use the same signal, CCP, PMW. Therefore, we've got the same PPS. But what we're going to do in our program down below is we're going to do the following. I have no idea what that's doing. That must be left over. Let's look at the main things first. This says hardware PMW, that's CCP1, hence it says number 1. I want a signal of 38 Hertz, and I want a duty of 50%, which is 127 in a byte. So if I take all this code here and just comment it out for a minute, program it, and we'll go back to the oscilloscope. There's the oscilloscope. We will see the same signal. However, the size of the code to get to that point has grown to 500 words, because you can change the duty and the frequency because it recalculates everything. And so one does it in a script which gives you 2 constants that control it, and this is in assembly. So let's have a look. So basically, same thing. Here's the same command we're heading towards at the bottom, but we're going to pass it a value at the bottom here. And it says here, define it. I don't know why it's there. But that's not very nice, really. That should be there, really, shouldn't it? Read the value of the AD that we got attached, wait 10 milliseconds, and then put it on the change the ADC. I don't like that code at all. Don't know when this was written. A long time ago. Read the AD, put it in there, set the ADC. This is not very nice, to be honest. We ought to change this a bit. Dim. We shouldn't be changing the duty cycle every few milliseconds. It's just not the way to do it. So I'm just going to go old ADs. I can do it here. Look, I can go old AD. Is it ADC val? And what I'm going to do, I'm just going to store things. I can put a 0 there to make sure it's initialized as 0. And I'm going to go down here and go, if the new ADC value, which is the one that's coming in, is not equal to the old ADC, that means it's changed, then update the signal. And then I just need to set the old ADC value, the ADC value. That's better. That's much better. Let's program it. Look at the oscilloscope. This worked anyway. Let's go out to webcam. Let's go out to desk cam. Okay, desk cam. There we go. Look. Rotate the part. Signal goes down. Eventually, it's just the oscilloscope. It's got a bit of a latency in it. Oh, look at that! You got beautiful signals, and then it goes flat because it's full on. Look at, and in the code you can output those values to the ADC and the serial if you wish. Okay, not really bothered. You do it. Now, what's important here is that I am changing the duty cycle, and if I can change the duty cycle, I can change the frequency, which I won't. That's not the. I just wanted to show you. That is a lot of that assembly has been generated in the library for you, but it shows you where you can generate a signal. Let's go back to the code, desktop. 16-bit PMW. Oh wow, 16-bit. What's this? Let's just look at the way it works. I'm just going to compile it to start with, and then we'll go Has it done it? Done it. It looks like the same signal. Looks like the same signal. All right, it does the same thing, look, but this is 16-bit. So I've got lots more. I have got a lot more granularity in that signal. I've only got 15 steps, 255 steps in the other model. I've got so many in my PMW module, 16 bits. You work it out. Now, we haven't written a library for this, but I'm going to show you how you can do it because it's quite simple. First of all, PPS. There is a module called PMW, and you go into the PPS tool and you select your fields and you insert it in here, not the CCP one, but it's a different one. Let's have a look in here. Let's clear that. Look, there's one called down the bottom, and this is a different module. And what it is that, oh, you can't see. Let me just zoom in, bring it into focus. Can we see it? Oh, there we go. Beautiful. PNW 11. Is 11. Look, I've written to Microchip about this. It's just bonkers. PMW 11 and 12, PMW 21 and 22. Essentially, some of the, you have 4 channels here, but some of the parameters between anything that's like an 11 or 12 or 22 and 21, 22, they share parameters, like the frequency is fixed, but you can have different duty cycles. It is confusing, but they share parameters. And when you set it up, you have to be aware of what has been shared. But it's a different module to the CCP one, as you can see in the PPS tool. So you would come into here, select your output as RB, and add it in as you select RB and add it in as we were previously. I've done that, and I've left the serial code in here for so that you can debug it. Let's look at the code. Get rid of that. Okay, I am directly setting registers in the chip. They exist, so why don't I just set them? So in here, I'm saying select the external reset, select the clock source. I'm not doing auto loading. Set the PR cycle. It's like PR1 in the old timer sets to 6.3. This is the high byte. This is the low byte. 6.93. No prescaler. No postscaler. You can go have a look at this yourself. Okay. All right. I'm going to set it to 50%. So down here, I've got my 50% set. You have to go through, but this is a really good reference because this works. So you can use this as a basis. Clear a load of interrupt flags, just need to be cleared. And then finally, I just enable it, which is the last bit, which is bit 7, by the way, just so. Now, the main code looks like the following. I've said my duty is equal to a word, but it aliases those 2 registers that we have set. Let's have a look. Okay. Oh, let me just take that. Control C, Control F. And if I look up here, it's one of the registers that exists. So I can actually create a variable that's used as a variable that actually addresses 2 registers or more registers, or 1 register, depends what you want to do. But this alias says whenever I set my duty, it will update those 2 registers accordingly. My frequency is a word aliased 2 other registers. Oh, and then you'll see the old value and ADC value as words. So what I'm going to do is I'm going to read the ADC as a 10, and then I'm going to scale that number. It's in a range of 0 to 100 and 1023 to my frequency, because I know that my frequency is the upper limit. And then if it has changed, all I'm going to do, because I'm using registers as my aliases, I don't have to set them. They are here. We'll look at this in a moment in assembly, so we understand it in detail. But what you have to do is there is a bit that you need to set called LD_PM1 for PWM1 control. If you set that to 1, it loads the duty register, and on the next period event, it will then change it. So you're not doing any heavy lifting here. Most of the heavy lifting is being done by the aliases. So let's just make sure we understand what we're saying. If I change the potentiometer, the LEDs and the oscilloscope definitely works, because it's definitely doing it. So if we look at, let's look at this piece of code here in assembly. So we can have a look at. Don't worry about this. Don't get scared of assembly. It's a good reference point. Says it can't find it for some reason. Am I in the right file? Let me just compile it. Definitely compiled it. Shift F7, open up the assembly, do a search, and it says it can't find it. Oh, I know why. Because I've got my search criteria in here is set to regex. So I'll just put it back to normal, do a search, and it's found it straight away. So look, here's the call. It says read the AD 10, go and get a 10-bit value, and put it in that variable. Look, it goes and does the function, goes and reads the AD, and then it says here, whatever value came back, go and put it in here. Ooh, that looks a bit weird. So that says system read 10. That's the value that comes back from the function, and it says put it in ADC val and ADC val H. But that could be RAM. Control C, just to Control F, just to see what that equals. I'm just doing a search. Where's my alias? Oh, here it is. Here, look. It's aliased a bit, 316 and 317. I wonder what they are. Okay, let's figure that out. PIC18. Let's just click on, I've selected the right chip, GCBASIC ID8, and we'll open up the data file for this chip. Then we can do a search for that number. What was that number in the assembly? I thought I'd taken a copy of it. 317. Oh, I've got this search still set. Well, I was struggling there because I've got it all wrong. My duty, let's look at that again. My duty is alias to these two registers. Let's look at the assembly. That is my duty. The low byte is 1131. The high byte is 1132. I've opened up the DAT file. 1131 is that byte, and 1132 is that register and that register. So whenever you refer to my duty, it will automatically update the registers. Really important. You don't have to have a different piece of RAM and keep copying variables about. Really simple. Back to PowerPoint. There's PowerPoint gone. So we have seen many different methods of using pulse width modulation. I've walked the examples. I've showed you the results on the X-Minilab scope. Next time, we're going to use millis. Enjoy.